All right, so 3/8 is the tangent function, and there's a lot of stuff about tangent in here. When we did sine and cosine, it broke it down into parts. It did like the sine and cosine, like how to find sine and cosine from a coordinate point, how to find sine and cosine from the unit circle, and then we got into the graphs of sine and cosine. Tangent, because it's just one function, they put everything together. So we're going to review how to find tangent given a coordinate point, how to find tangent using a unit circle, and then how to graph our tangent curves. So we start with the tangent function, like just definition. If point P is located where the terminal ray intersects the circle and the radius of the circle is r, then the tangent of the function, which gives the slope of the terminal side. So you're going to see a question that says, what is the slope of the terminal side? And it means, what is the tangent? Those two things mean the same thing. And the way you find it is either y over x or sine over cosine. So all this top part says is if point P is located where the terminal ray intersects the circle. So if I had an angle formed and the terminal point intersects the circle, that's where you're going to get your xy. And then to find the tangent, we just put y over x. So a question will look like this. The point P on the terminal ray of the unit circle has the coordinate points of 3/5 and 4/5. Find the tangent of theta. So I'm literally doing 4/5 over 3/5. I flip it. 4/5 times 5/3. The 5's cancel and I get 4/3. So that is not only the tangent of the function, but is also the slope of the terminal ray. Those things mean the same thing. AP questions in the homework use both of those terminologies. It's the same thing. Easy stuff, right? We're good? All right, then we get to the tangent of a unit circle angle. So your AP exam can ask you for the tangent of any angle on your unit circle. So hopefully we still have this memorized, okay? We talked about it before, but our x is our cosine, the y is the sine. If I want to find the tangent, I could put the y over the x, or you could memorize at least your first quadrant and then the quadrant angles. So let's start with those. If I go to the right here at 0, and I ask you for the tangent, you'd put 0 over 1, and that would be what? 0. If I go to the left, I get 0 over -1, same answer, 0. So tangent 0 at the right and the left. What about top and bottom? If I do 1 over 0 or -1 over 0, what do you get? Undefined. Which is going to lead into our tangent curves in a little bit. And then our over 6, if I put 1/2 over √3 over 2, I end up with 1 over √3, and that gets rationalized to √3 over 3. So the over 6 is √3 over 3. The over 3 is √3. It's the reciprocal of it. And the over 4 is 1. So remember the trick to learning the √3 and 3 and all that stuff is over 6. The denominator is 6. It takes 2 3's to get to 6. And the over 3 is just 1 3. And as you go around your unit circle, all students take calculus. Anything that's in the second quadrant and the fourth quadrant is going to have a negative tangent. So same values, but negative. Anything in the first and the third are going to be positive. Good so far? Yes? Okay, so example 2 says, in the xy plane, an angle, which is missing the E, an angle theta in standard position has a measure of theta equals pi over 6. Find the slope of the terminal ray of the angle. What does the slope of the terminal ray of the angle mean? Good. Find tangent. Tangent at pi over 6 is √3 over 3. There's an AP question on your homework like that. It is that easy if you know your unit circle. Questions on that one? All right, now we're going to graph it. So the graph of the tangent function looks like this box here. There are vertical asymptotes, and this is your parent function. There are vertical asymptotes everywhere on your unit circle. Our tangent was undefined. So if you think about at the top, it was pi over 2, it was undefined. At the bottom, it's 3 pi over 2, it was undefined. And in cyclical motion. It would continue to happen in that pattern. So that's where those asymptotes come from. Undefined on a graph means asymptotes or holes, but in this case, asymptotes. So that's where they come from. And this is, again, parent function. We're going to learn how to shift them in a minute, but this is the parent function. Then the curve occurs in between them. It rises to the right and falls to the left. Those would be arrows at the top and the bottom. The point halfway between the asymptotes is your x-intercept. And the quarter point and 3/4 point are where your A value is. So this is A and this is negative A. This is negative A. This is positive. What did I put there? There and there. Negative A and positive A, like that. So initially, it is just 1, because your A is 1 on your parent function. But that's how a vertical stretch is going to cause something. Obviously, we're not changing an amplitude because there's no amplitude here. The A is your quarter point and 3/4 point. So if you look at the top, it says the period is pi. Instead of 2 pi, the period is pi for tangent. Again, this is just for our parent function. We're going to edit that a little bit when we start to shift things. The graph has a vertical asymptote at pi over 2 plus k pi, where k is any integer. What this means is if my first asymptote is at pi over 2, then I can add 1 pi and I'd get the second one. Or I can take away pi, so I can make it negative 1 pi, and I'd get the other one. I can keep going like this in a pattern. If I keep adding multiples of pi, then I'm going to keep getting my asymptotes. And the domain, and this is important because it's a typo, theta does not equal those same points. So the domain is that theta cannot equal everywhere there's an asymptote. Your graph would start and stop. And your range, because those arrows point up and down, your range is all real numbers. On the right is just some other information about your tangent graph. This graph would be increasing as I move from left to right. So it is constantly increasing. It stops and then starts again, but it's still increasing. So the whole thing is increasing. If it had a reflection, now it'd be decreasing. Like if this was flipped upside down, now it'd be decreasing. And then the graph of the tangent function changes from concave down to concave up in between those asymptotes. So if I were to look at this graph, this first part is concave down. The second part is concave up. And the place it changes from concave down to concave up is your x-intercept. So in that case, it would be concave down from negative pi over 2 to 0. It would be concave up from 0 to positive pi over 2, and it would keep repeating that pattern. So if it asked you, like, is it concave up or concave down from negative pi over 2 to positive pi over 2, you'd say both. If it was from negative pi over 2 to 0, it's concave down. If it's from 0 to positive pi over 2, it's up. Questions on that one? All right, then we're going to find the period and the asymptotes if they shift away from your parent function. The period is pi over b, so b is going to be next to theta inside your tangent function. It could be like that, or it could be b theta plus c, like that. Either way, the b is what's attached to the angle. So I do pi over that to get your period. And then there's 2 ways to find your asymptotes. We're going to kind of talk about both ways. One is to graph your original parent ones and then shift them to the right and to the left if there's a phase shift or a period shift. The other way, which I think is more straightforward, is take your bx minus c and set it equal to pi over 2. And that will give you your first asymptote. And then you're going to take that and add the period and subtract the period, and you're going to get 3 asymptotes. So whatever is inside the parentheses, like if it said 2 theta minus pi, let's say, then step 1 is set that equal to pi over 2. So I would add pi. I'd get 2 pi equals, this is 2 pi over 2, 3 pi over 2. And then divide by 2, multiply by half. And my first asymptote, which is really the middle one, would be 3 pi over 4. So that would be step 1. Step 2 is find your period. So this case, it would be pi over 2 because b is 2. And then step 3 is add and subtract your period from the middle asymptote. So I would take 3 pi over 4 and I would add pi over 2. And I would take 3 pi over 4 and I would subtract pi over 2. So I'd get 2 pi over 4 here. I'd get 5 pi over 4. 2 pi over 4 here, and I get pi over 4. And you'll have 3 asymptotes. So when we did this in Algebra 2, you needed 4 asymptotes. We added the period, subtract the period, like that. You can just find 3. So it's going to ask you for 2 periods, which is 2 curves, and 3 asymptotes. So I can go through those steps. I could literally find the middle one, which was that 3 pi over 4. Find the middle one. Then go to the right, the period, which is 5 pi over 4. And then go to the left, the period, which is pi over 4. And now you've got your 3 asymptotes. And then you draw your curves in between. We're going to get a little bit more specific on the curves in between, but that's the general idea. If you are more like visual, if you want to take your asymptote and say my original asymptote is at pi over 2, and I want to shift this, let's say in this case our shift was a positive pi over 2 to the right, I can shift, I can shift my asymptote to the right. So you can visually shift it, it's the same idea. Here, make sure you add the interval of k over b. I was on the last slide, okay? So if it asks for the period and it wants it in interval form, like that's the kind of the wording on the question, you'll see it's a multiple choice on your AP, and you just want the interval included, then you have to add that k over b. All right, so from our equation, find the period of the function. The period is pi over b. What's b in a? 4, so this is just pi over 4. What's your b in b? 6 pi. So pi over 6 pi is 1/6. Your period does not have to have a pi in it. Neither does your asymptotes. They don't have to have pi. There's literally an AP question on like B in your homework today. Now what you also have to consider is the interval. So normally we add k. So if I wanted the interval here, I would add k over 4. And here I would add k over 6 pi. So if it wants just the period, then I do pi over 4. If it wants to know where the asymptotes are, I have to add on the interval like this. So period is just pi over b.
So the
K over b is where all the asymptotes are going to occur. All right, now look at C. They're all different colors, but here's all my asymptotes. If I want a period, I could literally pick any 2 consecutive asymptotes and find the distance between them. So if I want to go positive, I could go 3/4 minus pi 4, 3 pi over 4 minus pi over 4. I could do pi over 4 minus a negative pi over 4, any of them. Just pick the ones that are consecutive. 3 pi over 4 minus pi over 4 is 2 pi over 4, which is 1/2. So you pick any 2 asymptotes and find the distance between them. All right, vertical, yep, sorry. All right, now we're dealing with a vertical and horizontal translation. So this is a shift up or down and then a shift left or right. The vertical always happens after the function. If I add or subtract a number here, it's a vertical translation. It's exactly the same with tangent. So if I add 1, I add 2, I subtract 3, I'm taking my x-intercepts that were normally at my y on my x-axis and I'm shifting them up or I'm shifting them down. True to the sign that's there. And just like every other function, if it's inside the parentheses, it causes a horizontal translation. Now notice that this time they wrote x or theta plus c, but then the translation is negative c. So it's still the same as it's always been. You still switch your sign. And when you move your horizontal, you're moving your asymptotes. So the vertical asymptotes move horizontally with two things. One, they originally are set up differently by a period change. Two, they will shift right or left by a phase shift or a shift on the C. And that's the horizontal translation. All right, example 4 says, use the red curves as the original graph. Describe the vertical or horizontal translation of the tangent function. So looking at A, the red is my original. What it moved to get to the B? To get to the blue. It was a vertical shift, specifically how many? 40. Up, good. Up to, I know the lines look like they're 2, the 4, but they're not. Okay, so this is a vertical translation. Up 2 units. So on the equation, this would have said tan of theta plus 2. Well, y equals, or f of x equals tan of theta plus 2. B, look at B. What happened from the red to the blue? It shifted to the right, and we went to the right, we went to the right, we went to the right. So it's a horizontal translation. Now my point of intersection, or my x-axis, or my x-intercept, went from 0 to this point right here, which would be what? Pi over 4. So this is a horizontal translation. Right, pi over 4. So my equation would be tan, in parentheses, theta minus pi over 4. Good so far? Yeah? Okay. All right, now multiplicative transformations are your dilations. So this is your stretch or your shrink. If it's in the front, so this is based on your A value, it's a vertical dilation, and we ignore the sign. It's a factor of absolute value of A. So if it's a negative 3 in the front, we just say that that's a factor or a vertical dilation of 3. And the negative would have this impact, right? If A is less than 0, there's a reflection over the x-axis. So my curve that normally goes up to the right and down to the left switches if it's a negative A. That vertical dilation is where your quarter point and your 3/4 point go. So if I have my graphed function, if I have an asymptote here and here, let's say, this would be my x-intercept. I would eyeball the quarter and the 3/4. And then instead of, let's just say it was a 4 tan theta, instead of going up and down 1, I'm going up and down 4. So I'd be going 1, 2, 3, 4 here, and 1, 2, 3, 4 here. It's going to cause a vertical stretch. If it was a fraction, then it would cause a vertical shrink. I would only go up and down a half. If the B is something other than 1, then it causes a horizontal dilation. And just like everything else, we do the reciprocal. So if it said tan of 4 theta. This is a horizontal dilation by a factor of 1/4. It's going to cause your period to change. So that's your B, right? It would now say your period goes from pi, so from negative pi over 2 to positive pi over 2 is my original. Now it's shrinking it. It's making it pi over 4. The whole thing would get completed in pi over 4. If it's still centered, it means it would go from negative pi over 8 to positive pi over 8. So that curve that would have originally been here is squished here. Remember, a horizontal compression looks like a vertical shrink, right? It gets squished, it gets stretched. You don't have to worry too much about that. Like, I would say know it from your equation, but like if I gave you the equation to describe that dilation, you should be able to describe it in words. But if you're going to graph that, you're going to find your period and you're going to find your asymptotes algebraically, and then it will take care of your horizontal stretch or shrink. Xander. The new period, well, that would be pi over 4. If it was this, if it was 4 theta, then the period would be pi over 4. Correct. Which is, there's 2 ways to change the period. This says you can change the period by multiplying pi by 1 over b, or you could do what we just did, which is pi over b. Those are exactly the same thing. We never, if there is a sign on b, which doesn't typically happen, we ignore the sign, we just take the value. And notice this equation, the b is separated out like it was for sine. If I have a b and a horizontal shift, I'm going to keep them separate just to make it easier. You could distribute that in, but you might as well just save yourself the trouble and keep it separate. So if I'm finding an equation and it has a horizontal dilation and it has a phase shift or horizontal shift, then I separate them out. Make it easier on yourself. All right, example 5 says the graph of the tangent function is shown. Describe the transformation, then sketch the graph. So the original tangent function is there. And then I want you to graph 2 tan theta minus 1. What's the 2 doing? Vertical dilation by a factor of? Good. This is going to make it taller or stretch vertically. And the minus 1, what's that doing? Vertical shift down, or transformation down 1. So my original curve is there. My period did not change and there was no horizontal shift, which means my asymptotes will stay in exactly the same place. But my curve is going down 1, so all these x-intercepts are getting shifted down 1. And the quarter point and 3/4 point, instead of being up 1 and down 1, are going up 1 and up 2 and down 2. So from here, I would go down 2 and up 2, down 2, up 2, down 2, up 2, and here's my new curve, which is shifted down 1 and stretched vertically. Questions on that one? Means at the... All right, now we're going straight from scratch. So here's your function. You graph it without having an initial parent function to transform. So describe the transformation, sketch the graph. If I look at A, what's happening inside the parentheses? Good. This is a shift right, pi over 4. And outside, minus 1 is doing what? Down 1. Now I still have to, the A is still 1, which means my quarter point and my 3/4 point are still only up and down 1. There's no stretch here. But I still have to find the period and the asymptotes. So the period is pi over b. What's B? 1. So the period is pi. And then my asymptotes, like we said before, I can either make them my standard asymptotes at negative pi over 2 and positive pi over 2 and then shift everything to the right pi over 4. That's one thing. Or you could do it algebraically. I'm going to take what's inside my parentheses. I'm going to set it equal to pi over 2. And then what I get from here, I'm going to add and subtract the period from. So I would add pi over 4. This becomes 2 pi over 4 plus pi over 4. So my middle asymptote is 3 pi over 4. That's 1. And then from it, I'm going to subtract the period. And I'm going to add the period. So 4 pi over 4 here means negative pi over 4 is, not 6, 4 is another asymptote. And add here 7 pi over 4, or 1 3/4 pi, because those are the same thing, is my other asymptote. You need 3 to make 2 periods. How many of you remember this from Algebra 2, that part at least? Okay, good. All right, so I'm going to plot all 3 of those asymptotes. One's at negative pi over 4. One's at 3 pi over 4. And one's at 1 1/3 pi, or 1 3/4 pi. Now I'm going to find the point halfway between. If it asks for a specific intercept, I'd actually have to find that specific coordinate point, but for the most part, you're just graphing these. If I needed this specific point, I could add those 2 asymptotes, divide by 2, it will take me directly there. But if I could just find the center by visually, like finding the center, it's here and here, 4 little tick marks in each way. Split the center. And then 1/4 the way and 3/4 the way are where I'm going to plot my A. The A was 1. So 1/4 the way in, I put negative 1, 3/4 the way positive 1, 1/4 negative 1, 3/4 positive 1. So the -1 shifts everything down. So we could literally shift this down, this down, this down, this down, this down, this down, and shift it now like that. If you forgot to shift it like we did, like I did. Or before you plot those points, after you find your asymptotes, you could take your x-intercepts, shift them down 1. So it would be here and here. And then your A, 1/4 the way, 3/4 the way, 1/4 the way, 3/4 the way, down 1 and up 1, down 1 and up 1. So after you find your asymptotes, because the vertical shift doesn't affect your asymptotes, after you find your asymptotes, but before you plot your zeros, you could move it down or up if it was a positive. Okay, go to B. The negative on the front. This is a reflection over what axis? Good, over x axis. So instead of pointing up, right, down, left, it's going to go up, left, down, right. What's the 3? It's a vertical stretch or dilation. Factor of 3, good. 2, inside. This is a horizontal. It would be a compression. We can say dilation, but it would be a compression by a factor of, good. That also changes your period, right? Because B is 2. So my period is pi over 2, which is going to be important when I go to find my asymptotes. Which is what we'll do next. So I'm going to find my asymptotes. I'm going to take what's inside those parentheses. I'm going to set it equal to pi over 2. So I divide by 2 or multiply by 1/2, and I get theta equals pi over 4. That's my middle asymptote. From that, I'm going to subtract the period, which we just said was pi over 2, and I'm going to add the period. So this becomes 2 pi over 4. This is negative pi over 4. There's my first asymptote. God bless you. And then 2 pi over 4, 3 pi over 4. There's my last asymptote. The period. Yep, from the first asymptote. So first asymptote is what you said equal to pi over 2, solve for theta, and then subtract the period from the one on the left, add the period to the one on the right. So now my asymptotes are at pi over 4, negative pi over 4, positive pi over 4, and positive 3 pi over 4. My x-intercepts are halfway between those asymptotes, so at 0 and pi over 2. And no vertical shift. But it's reflected, so I'm going up left and down right, and it has an amplitude stretch of 3, or an vertical stretch. So 1, 2, 3. 1, 2, 3 means the A is going up on the left to 3, down on the right to 3, negative 3, up on the left, down on the right. And there's your curve. So the last one flips it. It's going to give you the transformation, and it's going to ask you for the equation. So the transformations in the following order performed on the graph of theta, f of theta equals tan of theta, produce the graph of g of theta. A horizontal translation or phase shift to the right pi over 4, and a vertical dilation by a factor of 2. So where does the phase shift or horizontal translation go on your equation? Inside the parentheses. And if it's a shift to the right, what do you do? Negative. So this would be tan, in parentheses, theta minus pi over 4. There's my phase shift to the right. And then a vertical dilation by a factor of 2 would go where? On the front. Good. And we're going to call this g of theta because that's what it said. If it said a vertical shift, you'd add it to the end, right? If it said a horizontal dilation, so if it had said horizontal dilation by a factor of 2, where's that go? Inside the parentheses, and what do you do with that 2? Flip it, good. So it would be 1/2, so let's say it was all of that plus, that would be 2 tan, 1/2, close your parentheses, make life easier on yourself, because you don't need to worry about distributing that 1/2, okay? So if there was I don't know why I added the extra, there. If there was a horizontal dilation, separate it out, separate your B out like we did with tangent, with sine. If it was multiple choice and you saw that distributed, then you got to worry about it. But if it was just here's the equation, or give me the equation, then you can leave it separate like that. But you got to make sure you do the reciprocal. Questions?
What happens if you put it in the parentheses?
If you put it in, you just have to distribute it to both. So you'd have to alter the phase shift too. Does that make sense? Yeah.